Hi everybody, welcome back to another round of astronomy, and yeah, let's keep going. Last time we discussed how scientists reconstruct the CO2 concentration in our atmosphere. And I've left this up as a reminder, namely the amount of CO2 in the atmosphere as a function of time, going back almost a million years. And the last point I highlighted was that today we sit somewhere around here in the 420 parts per million range. Well, what does that mean? If we have a higher concentration of greenhouse gases in our atmosphere, we should be able to predict some future outcomes. We know that greenhouse gases tend to prevent infrared light from escaping. So if we raise the concentration of greenhouse gas in our atmosphere, we should trap more of that infrared light, and therefore we should see the overall temperature of the Earth increase. So do we see that? Displayed in front of you is, on the horizontal axis, time, years. Okay. On the vertical axis, this is what's called the average deviation. So what I mean by that is, for the last 100 years, you take the average global temperature. That's represented by 0. 0 would be the average global temperature from the year 1900 to the year 2000. So it's a 100-year average. Okay. Then the next thing is, for each specific year, we're going to plot whether it was above or below the average. Okay. And of course, what average means is that you should have roughly the same number below and as above. Okay. That's what average is. So now, what do you notice about this chart? Yeah, you notice that the hotter years have occurred primarily since the 1970s, say roughly. Pre-1970s, we were basically colder on average. And since about the 1970s, you notice that we are dramatically warmer than the average. And it's not even just dramatically warmer. Unfortunately, you can also see that we are trending upwards, right? Ugh. That's not, I mean, if this were just a naturally occurring phenomenon, you would expect to see some sort of random behavior. Okay? And so, yeah, indeed, once by about the year 2000, 2010, the average temperature of the Earth was about a degree centigrade warmer than the 100-year average. That's 2 degrees Fahrenheit. Okay? Yeah. So if you have a higher concentration of carbon dioxide, that means you are trapping more infrared light. You're not allowing it to escape. That means that you see, according to our model, the average temperature of the Earth going up. Well, we can also, if the average temperature goes up, we can also identify effects that might have on our climate patterns. Now notice I use the word climate and not weather. Okay? There's a difference there. In other words, the weather is what you get. Right? If I wake up in the morning and I say, what's the weather today? Okay. The weather is what you get. I would argue the climate is what you expect. Okay. So climate deals more with longer term averages, if you will. Okay. Whereas the weather is the day-to-day kind of occurrences. Okay. You get a snowstorm in October. Okay. That is weather, not climate. In other words, that is a thing that occurs on a specific day. Okay? Climate would be more of an overarching thing. On average, over the course of all Octobers, would I expect to get snow? No. Okay. So the snow in October is just this like one-off, if you will. So if we have higher global temperatures, what kind of consequences would we expect to see from that? Well, for example, you would have things like you're not going to see as much snow, right? And on average, if the temperatures are higher, you would expect the amount of snow that you get, or maybe I should be more specific, I'll say the length of winter, you would expect it to become shorter. Well, one of the consequences of that would be something like glaciers. How do we measure snowfall? Go and look for sheets of ice, right? Sheets of ice, glaciers, are formed by having progressive layers of snowfall compacting into ice. So if we expect a shorter season for snow, we would expect also to see that glaciers recede. There's not as much material to rejuvenate the glaciers. In the course of 10 years, this glacier has receded to the point where it's almost not on the lakeshore anymore. And unfortunately, we're seeing this worldwide. I picked this example, but we are seeing glaciers recede worldwide. Well, how about what else? Okay. I'll read this. Global temperatures. However, the continued warming that is projected to occur without substantial and sustained reductions in global greenhouse emissions is expected to cause substantial net damage to the U.S. economy throughout this century, especially in the absence of increased adaptation efforts. With continued growth in emissions at historic rates, annual loss in some economic sectors are projected to reach hundreds of billions of dollars by the end of the century, more than the current gross domestic product of the United States. Okay. What we're saying here is that, hey, these changes that we're seeing now are going to have dire economic consequences. Okay. For example, you have your glaciers melting. You say, I don't care about the glaciers in Alaska. Okay, that's fine. But those glaciers, that water has to go somewhere. That water goes into the oceans. So for example, if you have more water in the oceans, you would expect the level of the ocean to increase. Oh no, wait, there's more. For example, let me ask you another question. Water when it's cold as compared to water when it's warm. So if I take 1 cup of water at the same temperature and I heat one of the cups up, not to boiling, but let's say I just heat it up to halfway to boiling, which will have the larger volume? Yeah, remember that when you heat up an object, the atoms are moving faster, which means the warmer of the two objects will have a larger volume. Right? The objects are moving faster. It's still liquid, but that means that if the molecules of water are moving faster in the warmer liquid, that means that there's a small increase in volume. So not only are we depositing more water into the ocean, but the temperature, the increased temperature of the water will cause that water to expand slightly. So you've got a double whammy here. You have more water, and that water is larger, the volume. Okay. So let's tie that into economic impact for a moment. Okay. That means you have a larger volume of water in the oceans, which means the level of water goes up. There's a projection that the ocean, the water level in the ocean has already gone up something like 2 inches in the past century. And it could be as high as a meter. Okay? At least. You go up 1 meter, unfortunately, you're going to say goodbye to a lot of the coastline of the United States. It's going to look dramatically different than it does today. Okay? In fact, this problem is already an issue. Look at places like Venice. Okay? Look at some of the low-lying islands in the Pacific Ocean. Okay? They are already seeing some of the effects of this increased volume of water in the oceans. And it's only going to get worse. If you melt the entire Antarctica ice sheet, I can't remember exactly, but it's projected to rise this ocean, I can't remember, like more than a meter. Okay? There's a tremendous amount of water locked into the ice sheet. You dump that water into the ocean, you're going to see some profound consequences. Okay? Sorry, I'm on doom and gloom wreck today. Well, what else do we have? Okay. How about the regional fire season? Okay. With the increased temperature, that means that you have shorter periods of winter, cool, wet season, and a prolongment of hot weather, which generally corresponds to drier conditions. Okay. So what I have up for you here is the change in length of the fire season. And right now it's in days per year. So anywhere where you see red, you are seeing the fire season being prolonged. Okay? Notice that you have places like the rainforests in Brazil. You have places like the west coast of the United States, okay? And also the east coast of Africa. Okay? You're seeing a prolongment in the fire season. Hot, dry conditions. Okay? We've already mentioned flooding. If the sea level goes up, okay, then you're going to have coastal flooding just due to the volume of the ocean increased. But you also have other effects. For example, okay, let's say warmer water means that you are going to have more water evaporating off of the surface of the ocean. Okay. In other words, the water being warmer puts more water vapor into the air. So when it does rain, those rains are going to be more severe. There's more moisture in the atmosphere so that when it does rain, you're going to get more water dumping down. So ironically, even though you're going to look at hotter and drier conditions for a longer amount of time, an increase in the fire season, for example, you are also going to see an increase in rainfall, right? Because there's more water moisture in the air, which means when it rains, you're more likely to have some sort of flooding effect. Sea level rise. In addition to the sea level rise, okay, you also have something called acidification. Warmer water, not only does warmer water cause more water vapor to go into the atmosphere, that drives the storms, okay, but in addition to that, warmer water is good at absorbing other things. Don't believe me, it's ironic, but a bottle of pop, okay, soda, if you prefer, or Coke, depending on where you're from. Bottle of pop, soda, or Coke, whichever you prefer. Okay. You open up that bottle, you get that tss, right? What's happening? It's some of the carbon dioxide that is confined to the liquid is escaping. Okay. Of course, the canonical example of this, you can get all of that carbon dioxide to kind of release all at once. It's a really cool chemical process, right? That is a chemical reaction that is causing all of the carbon dioxide that is inside the liquid, that has been incorporated into the liquid. It's a way of getting it to release all at once. Okay? So why do I show this? The idea is that water can absorb carbon dioxide as well. Okay? And we have a huge body of water, the oceans. In fact, by some estimates, the oceans contain more carbon dioxide than all of the plants on the surface of the land. Now, a warmer ocean means that it can absorb more carbon dioxide. You say, well, that's not a problem. Life is good. Say, hey, bear in mind, you go to the dentist. They're cleaning your teeth. And some of the things that they ask you, are you flossing daily? Are you brushing daily? Okay. Do you drink a lot of pop? Why are they asking you about pop, soda? Yeah, part of it is the sugar. Okay, that's always bad for your teeth. But even if you're drinking diet soda, so pop is still bad for your teeth. Why? It's because that carbon dioxide that is in the water forms what's called carboxylic acid. Okay? You actually, when you absorb carbon dioxide into water, you form a little bit of an acid. And that acid eats away at your teeth. Okay? The calcium structure of your teeth, when you drink a bunch of acid, soda pop, Coke, okay, you are eating away at some of the some of the calcium on your teeth. Okay? Acid is a very bad thing for calcium. So why do I care about ocean acidification? There are a lot of things that live in the ocean that use calcium. In fact, calcium is how a lot of creatures make their shell. Okay? Calcium is a lot of, for example, what the Great Barrier Reef is made out of. Okay? When you acidify the ocean, you are damaging animals, creatures that use calcium for their structures. Okay? Shells, reefs, etc. And if you kill off the reef, then the next thing is all the animals that are living in the reef die out. You destroy the entire ecosystem. So again, ocean acidification is driving some of these ecological changes that we see. So it's a double whammy on the ocean. Turns out the Great Barrier Reef is very sensitive to temperature and acidification as well. And we are seeing bleaching of the Great Barrier Reef. So where do we go in the future? Okay. Put in front of you are some different projections, some different hypotheses. And let me kind of explain where they come from. The idea is relating carbon dioxide concentration to global temperatures. We know that the increased amount of carbon dioxide will affect the temperature via the greenhouse effect. Right now, the question is, by how much? Now, I've glossed over a lot of other things with a broad brush. For example, ice tends to reflect light very well. So if you have sunlight striking the surface of an ice cap, rather than that light being absorbed and re-radiated as infrared light, it just reflects off. Okay? And of course, if it stays as visible light, then it will pass back through the atmosphere and everything's hunky-dory. Okay? So for example, there are models that take into account the amount of surface ice on the Earth. For example, there's other models that are trying to get an understanding of how much cloud cover we could expect. If you have more water vapor in the air, you would expect to see more clouds. Clouds tend to be white, and so sunlight striking the top edge of a cloud gets reflected, and again, you don't tend to have that absorption and re-radiation of infrared light. Okay? So there's a lot of stuff that I've glossed over. I'm trying to give you kind of the basic underlying idea. Now, let me look at this left chart. Okay? You see blue line, green line, red line, and they're all labeled. RCP stands for Representative Concentration Pathway. Okay? It is indicative of, for example, all of those little ideas that I've told you. The amount of carbon dioxide in the air. It's trying to take into account clouds, ice, variations in the temperature of the sun, etc., etc. You could think of it as a different way is how much energy gets trapped by the atmosphere of the Earth. Okay, that's a different way of thinking about it. Now, what you're looking at here, 3 different projections. Right now, 2013 is where we sit, and there are 3 different models, and there's more than 3. This one just shows the 3. And it's based on what we currently know and the observations that we're seeing. Where are we going to go in the future in terms of temperature increase? Okay. RCP4 is right now we make some sort of moderate effort to decrease our carbon dioxide emissions. Okay? What does this mean? Turning off lights, maybe bumping up the thermostat a couple degrees in the summer, bumping it down a couple degrees in the winter, right? Trying to make an effort to be responsible for our energy consumption. Okay? RPC6, you don't try to make any kind of limits on your carbon emissions until 2080. So you see that RCP 4.5, you're making substantial efforts to curb your emissions by 2040, 2050. That's only 30 or 40 years down the road. Okay? If you say, okay, well, let's make it 50 or 60 years, okay, 2080, you'll see that the models that we're working with project something on the area of 4 degrees Celsius. Okay? Average increase. That's 10 degrees warmer, 10 degrees Fahrenheit warmer. So you think summer's hot right now in Indiana when it's 90 degrees. Imagine it at 100. Okay? RCP 8.5, business as usual. We burn the stuff like there's no tomorrow. Okay? And this is generally referred to as the worst case scenario. Okay? The gray banding, you'll notice there are various models for the business as usual. Okay? So the dashed line actually tells you the average of all the models that are used. So even the most optimistic model, and by optimistic I mean the smallest temperature increase, even the most optimistic model puts us somewhere at 7 degrees Celsius warmer in 2020 or 2200. Right now, RCP 2.6, nobody even talks about that anymore because as you've seen in some of our other charts, we're about 1 degree Celsius warmer than the century average already. This is no longer an option. Okay. RCP 4.5, we're at the cusp of not making that. Okay. As you've been aware, the United States has withdrawn from the Paris Climate Accords. What that is that was a voluntary agreement to curb our emissions. I won't go into the details of it. I'll leave that for a video or two. But at the end of the day, the United States has not made it a priority to curb emissions, at least in our commitment to other nations. Okay. Right now, we're looking at something like RCP 6 or RCP 8. Okay. You're looking at a temperature increase of about 5 degrees Fahrenheit by 2100. And also note about a half a meter of sea level rise. Okay, doom and gloom. The other problem that you'll see is that there's a huge misinformation campaign, I guess is the best way to say it. So I'm going to show a video here, and it's not to be, I don't mean it to be biased, but if we watch the video for a second, so look, I'm not going to argue the information. Let's assume for a moment that the information is good. Okay, so I'm not going to critique the information, but let's look at how the information is presented. That's the thing I'm kind of interested in. Okay, so take a look for a minute. Okay. So I'm always interested. My grandfather told me, he said, look towards the source from whence it cometh, still. And the still is very important. I like this video, not for the message that it sends, but I like it as an opportunity to kind of think critically about information as it comes in. So let's not argue the validity of the data. Okay, so I'm going to say, let's assume that the data that's presented in this video is correct. Okay? But I think that there's some very interesting omissions that we should think critically about. So, for example, let's say for a moment, I agree that since the 2000s, the United States has not increased in carbon dioxide emission. Okay? Let's take that. Yeah, perfect. Okay. In fact, that's probably true. Okay? Question. What's omitted? Or maybe a different way to say this. When would the United States have had a huge impact on emissions? Or a different way to say it. When did the United States industrialize? Not in the 2000s, okay? We're talking about they presented the data from 2000, but the issue is that the United States didn't industrialize in the 2000s. The United States industrialized way back in the 1920s, okay? Right? Henry Ford. Okay? You might even be able to go back into the Industrial Revolution, but the issue is that that's fine if you want to present the data from 2000. That data is probably good. The issue is that you've ignored the main part of when the United States contributed to climate change. Okay? So here's another question. Because the United States was early to the game, we industrialized early and then recognized the change. Okay? Here's an issue. Is it fair for the United States to tell other countries they can't industrialize? And I don't have a good answer for that, right? I mean, we know that it's bad to do carbon dioxide into the atmosphere, but is it fair for the United States to tell another country, well, we did it, but you can't. We did it and got an advantage. You can't do that, okay? Is it fair for the United States to tell other countries, no, you can't have reliable, electrical system or a reliable electrical production, or maybe a higher standard of living, okay? These are some major issues, and I don't have a good answer. Okay? Or for example, this shows the amount of carbon dioxide released by an individual in the United States as compared to individuals in other countries. Okay? Net emission by a country. And I agree, the United States is not the primary emitter of carbon dioxide, greenhouse gases in general. But look at the other countries ahead of us. Countries like China, countries like India. Okay? Yes, on an absolute scale, we do not emit as much as they do. But how many more people does it help in China or India as compared to the United States? Again, I'm not going to argue the data, but what I will argue is how the data is presented. Okay? I will say, for example, the United States is #1 in emission per capita. Okay? And there's other things like that. So the issue is that even if we don't want to argue the data, we have to start being very critical about how data is presented to us and ask ourselves, is this the right way to present it? Okay? I think there's another location. It's odd. At one point, they present an absolute number when they should be presenting a relative number. And there's somewhere else where they present a relative number when they should be giving an absolute. So it's very interesting. Put your thinking caps on when you see this kind of stuff. And it's a socioeconomic issue as well. It's a fairness issue. There's a lot of stuff tied into this. Okay? So where do we go? So you'll see this term thrown around, carbon tax. And what I would say is that we have not been taking into account the full cost of our emissions. For example, when I drive a car, I think about the depreciation on the car. I think about the insurance costs. I think about the gas, how much it costs to operate the vehicle or keep it maintained. What I have not been taking into account is the economic impact of the increased carbon dioxide concentration in the atmosphere. So if you prefer, that's what the carbon tax really is. It is an effort to take into account the full cost of burning carbon dioxide in terms of power production, electrical, in terms of driving a car, in terms of shipping items. Okay? It is, in some sense, it's very interesting. It is an economic solution to our problem. The more something costs, the less you tend to use it. Okay? If your electrical bill goes up by twofold, okay, you're going to use a lot less electricity. In fact, I saw it. I hated it when I was at the gas pump and gas was $4 a gallon. Okay? But I loved it in the sense that people were making conscious decisions not to drive their cars as much. Okay? So this is an economic thing. Now, please bear in mind, it's not saying let's go over and beyond. What it's saying is let's do true accounting. Let's take into account the environmental impacts to our carbon dioxide emissions. Okay? And you say, how do you put a price tag to that? Well, let's say, for example, that, and I hope this doesn't happen, but let's say, for example, New Orleans starts flooding every year. Okay? Well, how much does it cost to rebuild New Orleans? Let's take that cost and let's disperse it. Let's take the cost and let's divide by the number of gallons of gasoline sold in the United States. And we'll tack that on to the cost per gallon. We'll add on this tax, environmental impact tax, for example, to take into account the true cost of our decisions. And it's a cool thing, right? Because if that increases the price a little bit, that will also play into the consumer's mind about using less. Instead of driving over to Walmart 3 times a week, you might say, let me build a shopping list and just do it once. Okay? Or, for example, you do multiple errands at one time rather than separate trips. Okay? Now, to give you an idea, this was actually awarded the Nobel Prize in Economics in 2018 to William Nordhaus for integrating climate change into long-run macroeconomic analysis. That is, finding an economic solution to the problem. Okay? So I apologize for the gloom and doom, but I also think it's really important to kind of understand where the science comes from, where the observations come from, and see that tie in with both political and economic and probably social policy as well. So I thank you for your attention. I promise that the next one will be a little bit more chipper, and keep up the good work. I'll see you next time.